Okay, so in this video we're going to just quickly look at two example problems, one of how to deal with molarity and dilutions, and the other with how to go and proceed with a solution stoichiometry, in this case in particular an acid-base neutralization using molarity. So, the key to this is just remember that molarity is equal to moles per liter, and therefore moles of solute per liter is a solvent. Therefore, as long as you know the molarity and the liters, you can do molarity times liters, and that gives you moles. Now, that applies in two cases. In the first case, for dilutions, right, if we're looking at the moles as always being the same, when we're doing a dilution, we're simply adding more of the solvent. Okay, so if it was an aqueous solution, we're adding more water. We're not changing the moles of the solute at all, and therefore you can set up this, that the molarity 1, volume 1, so the initial molarity and volume, M1V1, molarity times liters is equal to moles. So moles 1 have to equal M2V2, moles 2. So because molarity 1 times volume 1 is equal to moles as long as you use liters as the volume, and molarity 2 times volume 2 is equal to moles, which have to be identical, you can set them equal, just plug in the 3 and solve for the fourth one. For solution stoichiometry, we're going to use that molarity times liters equals moles, and from there you can just do the stoichiometry, right? So if you get moles of A, you can just do convert to moles of B over moles of A, and if this was moles of A, we can now cross that out. Okay, same as any other stoichiometry problem. Alright, so let's go through two examples of these. The first example is starting with a 2.5 molar stock HCl solution. How would you make 200 milliliters of 8.75 molar solution? So we have a dilution case here, okay? We're going to have to add water because we need that molarity to go from 2.5 molar down to 0.75 molar. So I'm just going to set this up as M1V1 equals M2V2. Okay, again, it's always better to do volume in liters, just good habit to be in, because that way if you ever stop short and find something, sorry, 2.5 molar, find something and stop, you're going to end up in liters. You don't get confused. You could do it both in milliliters, but if you wanted to find moles, milliliters won't work. So I recommend you always keep it in liters. 0.75 molar, and volume 2 is going to be 0.200 liters. Alright, so we're going to try to solve for x to find out how many liters of that 2.5 molar stock solution we needed to dilute out to get to the 0.75. And so you plug that in and you solve and you get x is equal to 0.060 with the right sig fig, so therefore it's going to be 60 milliliters of the 2.5 molar HCl. Okay, now note it asks how would you make 200 milliliters of that. So what I'll do is we would take 60 milliliters of the HCl at 2.5 molar, and we would add 140 milliliters of water. Okay, because we need to have 200 milliliters at the end. So if you take this 200 milliliters that you're looking for, subtract off the 60, right? V2 minus V1 is going to be how much water you added. So right here is our answer. Here's how we would make up a solution of that. We would take 60 mLs of the 2.5 molar HCl and we would add 140 mLs of H2O. Pretty straightforward. Okay, let's look at a solution stoichiometry problem. Okay, so in this problem we're looking at how many an acid-base neutralization. So we have how many milliliters of a 1.50 molar barium hydroxide solution, which is a base, are needed to neutralize 200 milliliters of 1 molar nitric acid. Okay. First thing I want to do in this case is I need to convert things into chemical formulas and write out a balanced equation. So barium hydroxide, look on the table, barium is 2+, so it's actually going to be dibasic. It'll have 2 OH minuses with it. Okay, make it aqueous. We're going to add that to nitric acid. You need to know that that is HNO3. Make that aqueous. Okay, and we're going to form barium nitrate. Ba, and again 2+, so the NO3, 2, and we're going to form water. Okay, you always make water in a salt, that's going to be a liquid. Now we need to balance this out. Okay, the barium's balanced fine. Think of these things as units, so There's one NO3 minus on the left. There's two NO3 minuses on the right, so we need two of those. And then we have two OH minuses, two H pluses right there, so we're going to have to make two waters. All right, so we've got this balanced out. Now it's pretty much just a straightforward stoichiometry problem. Okay, there's really nothing different to this than when we did it with gases or with grams. Okay, so the first thing we need to do is go to moles. So we know we have 0.200 liters times 1.00 molar HNO3. Okay, and that's going to give me 0.200 moles of HNO3. Now comes the stoichiometry part, right? If you remember when I talked about stoichiometry, the first thing you do is get to moles. Done. Second thing, go from the moles of what you're at to the moles of what you want. Okay, well, 0.200 moles of nitric acid. I'm trying to convert to figure out the barium hydroxide solution, so there is 1 barium hydroxide mole for every 2 HNO3. Okay, so that is going to be 0.100 moles of barium hydroxide. Now at this point, the third step is just go to whatever the final answer is. So we're at moles of barium hydroxide, and I need to go to liters. Well, if you set up the molarity, you know that it's moles per liter, so 0.100 moles over x liters is going to be equal to the 1.50 molar barium hydroxide. Simply, you can multiply x over the other side, divide by 0.1 by 1.5, and what you're going to get is that x is equal to 0.0666, repeating, liters. So if we wanted to put this in milliliters, because that's what it asked for, you would simply say it's 66.7, rounded to 3 sig figs, milliliters of 1.5 molar BaOH2, barium hydroxide. Okay, there's our answer. That's how you solve this.